Carpenter X. Hello everyone, welcome back to another Carpenter examples tutorial. Here we have an Ansys Workbench study to conduct a thermal analysis of a heatsink. We are going to conduct our study in three parts. Firstly, we'll do a steady state thermal analysis. Secondly, we'll do a transient thermal analysis. And thirdly, we'll conduct a thermal stress analysis. Our heatsink is made of aluminum, and the properties of such is that we apply a thermal conductivity of 170 watts per meter Kelvin and also a density of 2,800 kilograms per meter cube, and we'll also apply a specific heat of 870 joules per kilograms kelvins, and also we'll add a thermal expansion coefficient and a Young modulus of 70 gigapascals and also a Poisson ratio of 0.3. We're going to bear in mind that the fan forces air over all surfaces of the heatsink except for the base, and at the base the heat flux is 1000 watts per meter square, and the surrounding air is 28 degrees Celsius with a transfer coefficient of 30 watts per meter square degrees Celsius. Let's jump over to Ansys Workbench and get this done. Let's begin by creating our steady-state thermal analysis. So we can do that by navigating to Toolbox, Analyze Systems, go down to Steady-State Thermal, hold and drag and drop that into our project schematic. Now we need to add a material, so we have to double click on engineering data and let's click on this blank cell here and let's enter the name of our material, which is aluminum. Now make sure aluminum is selected and let's navigate to our toolbox, expand thermal, and let's add a isotropic thermal conductivity. So double click on that, and we need to add a value, so double click in the value cell and enter 170. Okay, we have our temperature in Celsius, but we want to work with Kelvin for this part of our study. So let's go to our toolbar, units, and here you have metric. Let's go to SI, and also make sure you have display values in project units. So select SI here, and now we have it in kelvins. Let's close engineering data, and we need to create our geometry. So we can do that by double clicking on geometry here, and this will load space claim for us. Now that space claim is fully loaded and ready for us, let's go to File, let's go to Space Claim Options, and we are going to navigate down to Units. Make sure the type is metric, the length is millimeters. Let's scroll down to check our grid. So grid here, minor grid spacing 1 millimeter, click OK. Now let's add a new sketch plane. We can do that by selecting here, or we can right click in our graphics window and select new sketch plane. If we move our mouse around, we will see different options, but we want the XY plane, so let's select this by simply clicking in our graphics window, and that's left click, that is. Okay, with that selected, let's hit V on our keyboard, which will take us to a plan view, or you can select plan view from here or here. Okay, and let's select line in Sketch. We have line, and let's click the datum point, and let's move 11 units to our right. And to see this better, pull your middle mouse button to U, okay, and click. Now we move up 3 millimeters, over 3 millimeters. Use Control on your keyboard and the middle mouse button to pan, and let's move up 8 millimeters. 1 millimeter to our left, 8 millimeters down, 2 millimeters to our left, 8 millimeters upward, and let's repeat the process. Okay, with that done, let's navigate to our design. So select design. Okay, if you want, you can hit escape on your keyboard, and let's click mirror. And now we need a mirror plane. So if you move your mouse button here, you will see we are selecting the X plane. Okay, but we want the Y plane, so let's select this one. Okay, and now we need to select our bodies. So simply left click here and drag over our entire set of lines. Okay, and once you let go, you see our geometry has been mirrored. Now we need to push and pull this. So let's right click and let's go to view and let's select home. Okay, let's go to our design ribbon and then let's select pull. Okay, and let's, once we carry the mouse over our geometry, we'll have the option to pull. So simply click your left mouse button here and hold and pull, then you stop, do not let go, and hit enter 15, and then you hit enter on your keyboard. And with that, we have created our geometry. So you can simply come here and hit home or H on the keyboard, and this is the geometry that we need. Now let's simply go back to our study, which is here. Okay, that's one thing in Ansys, it will open different windows. So as you can see here, for this window we have our geometry, and this window we have our study. Okay, now we need to set up our model. Before we do that, let's save our file. So let's go file, save, and let's navigate to wherever you want to save it. So I'm going to create a new folder here, and then I'm going to call it heatsink. Okay, and I'm going to double click in that to open a folder, and then I'm going to give my file name heatsink. So make sure you put the file in a folder and then click OK. Okay, and now let's create our model by double click or double clicking in this model cell, and that will start our mechanical. Now that our mechanical is loaded and ready for us to begin our study or set up our study, let's navigate to the geometry. So let's export geometry here. Let's select the solid, and for the material, we have material assignment, structural steel, Let's change that to the one that we set up earlier, aluminum. So select aluminum. Now let's navigate down to mesh. So we can right click on our mesh, insert sizing. Okay, and let's select our geometry. So let's navigate here and select the body option. So select body, and now we have the option just to click and select our entire body, and come here and you select apply. For the mesh element size, let's select here and let's enter 5e to the -4. With that done, we can generate from here, or we can right click on mesh and generate mesh. If we navigate down to statistics, expand that, and we will see the amount of nodes and elements that make up our mesh. Let's change our selection filter to face here by clicking here. Okay, and let's right click on steady state thermal and let's insert a heat flux. So select heat flux here, and let's use the middle mouse button, rotate, and select the base of our geometry. Let's go to geometry in our heat flux detail and click apply. And for the magnitude of our heat flux, that will be 1000 watts per meter square. Now, once we click steady state thermal, it automatically opens our environment, so we can either right click here and work, or we can work from our ribbon. So your choice. But this time I'll work from the ribbon, so I'm going to just simply select convection, and our convection has been applied here. So let's change the film coefficient to 28 degrees. Well, the 28 degrees goes to the ambient temperature, 28 degrees Celsius, and our film coefficient, that should be 30 watts per meter square Celsius. Okay, and now we need to select all the faces except the face of the base. Okay, so we can do that by simply coming to faces, make sure we have the faces filter. Okay, click in your graphics window, hit Ctrl A on your keyboard, hold Ctrl and deselect the base, and then come to geometry here and hit apply. So we have 29 faces. Okay, type convection, film coefficient 30 watts per meter square Celsius, and ambient temperature of 28 degrees Celsius. We can right click here and go back to our original isometric view. Now let's solve and retrieve our results, and we'll do this by clicking on solutions, and let's navigate over to thermal, and let's enter temperature. Let's enter total heat flux. Let's enter directional heat flux. For the directional heat flux, once that is selected here, navigate down to the orientation under definition. So definition, type orientation, and change the axis to the y-axis. And we can then solve by clicking solve here, or we can right click on solutions and select solve here. Now that our solution is finished, let's click on temperature and let's come to edges and select no wireframe, and here we can view our temperature distribution across our heat sink. You can also go to the graph, and if you hit play, you can see the changes of the temperature over a particular period of time. Let's hit stop, and if we hit the tabular data, you can see the minimum, the maximum, and the average. Okay, let's navigate down to the heat flux, and if you select vector, so let's close this for now. Let's rotate, let's zoom. Okay, you now have the option to display the direction of our heat flux. So you can see the different arrows. If you want the arrows to be tick, you can select here, make them solid. You can increase the amount that you want to show, and you can decrease the amount that you want to show. You can make them uniform, and you can make them a bit more spacious. Okay, so your choice here. All this is your choice. Okay, now let's navigate down to the directional heat flux, and we can change the from contours to isolines, and this gives you a better idea of what is going on in terms of our temperature distribution. So this concludes our steady state thermal analysis, and we'll then go to our second part, which is part B, to do the transient thermal analysis. Let's navigate back to our project schematic window. Okay, and we need to drop a transient thermal analysis system into the solution of steady state thermal. So use your left mouse button, hold it, drag and drop it into solutions right here. This creates a transient thermal system that shares data with steady state thermal system. The temperature distribution from the steady state thermal analysis is now the initial temperature for the transient thermal analysis. Now let's add some material properties. So let's double click on engineering data in steady state thermal. Let's select aluminum. With aluminum highlighted, let's select the material field variables, and here we have physical properties and we have our thermal properties. Okay, so let's double click on density, and let's add 2,800 kilograms per meter cube. Let's click our material fields variables again, and this time let's add a specific heat constant pressure. So let's double click on that. Let's double click inside of the cell for value, and let's enter 870. Okay, and let's change the units here to SI, so we'll have joules per kilograms kelvins. Okay, Let's close engineering data here. Now that we are back to our project schematic, let's double click on Setup inside of Transient Thermal, and it says upstream data needs to be reread or reread. Would you like to read the upstream data? So let's click yes. And this will start our mechanical. Now our mechanical is loaded and ready, so we can set up our transient thermal. So let's firstly close the steady state thermal study. So we will focus on the transient thermal study. Select analyst settings, and we're going to manipulate our details here. So for step controls, number of steps, let's make sure that is 1, current step number 1, and we have step end time. Let's change that to 180 seconds. And for auto time step in, let's change that from program control to on and define by time. That's okay. Initial time step, let's change that to 0.1 second, and the minimum time step, let's change that to 5 e to the minus 5. Okay, and for the maximum time step, let's change that to 5 seconds. Okay, let's change the minimum time step a little bit. Let's make that 0.005. Okay, 0.05. Now let's continue by inserting a heat flux. Okay, so this would be basically applying the cycling heat flux. So let's right click on transient thermal, insert heat flux, and for the magnitude here, let's change that to tabular. Okay, and for the geometry, let's make sure we have the face filter selected here, and rotate using the middle mouse button, and click the base, come to geometry, apply, and you can always right click and go back to isometric view. Okay, let's select tabular data here. If your tabular data is not showing up here, sometimes it might be here, depends on the settings. But even though once you are in the environment, heat flux is selected, you have the option to turn them off and turn them on from here. Okay, so select graph, you'll have a graph here. I'm going to unpin that, then it will come here, tabular data. I can do the same, and if I unpin it, it will come here. So I need it, so I'm going to select it, and then I'm going to pin it. Okay, and now I'm going to manipulate these or add. So let's enter our values. So here, click in the blank space and enter 45. Heat flux is 0, so that automatically goes. Here, let's enter 45.1. Heat flux is 1000 here, so let's go here, 1000. And let's just manipulate this 180. Not really manipulate, but we're going to add a value for at the 180. So let's add the 90 there, and let's add 1000 here. Okay, and as you can see, the 180 falls below and it says equal 1000. So that is fine. Now let's click in this empty space, 90.1, and that will be 0. So let's manipulate that here and enter 0 for that. Let's click in this empty space again, and let's enter 125, 125, 0, 125.1. Let's enter 1000 for that value. And that should be it. So let's double check. 0 at 0 seconds. At 0 second, the heat flux should be 0. 45 seconds, it should be 0. 45.1, 1000, 90, 1000, 90.1, 0, 135, 0, 135.1, 1000, and 180 equal 1000. So that looks good. Let's now insert our convection. So we can get the convection boundary condition by right clicking on transient thermal, insert convection, or we can get it from our ribbon. Okay. For the film coefficient, let's enter 30 watts per meter square. 30, enter. And for the ambient temperature, 28 degrees Celsius. Okay, and we need to select our geometry, so make sure you have face filter selected and click in your graphics window, Ctrl A on your keyboard, rotate, hold Ctrl and deselect the base. Okay, make sure the base is deselected. It will turn gray once deselected, and come to geometry here, apply. Okay, and then you can right click and you can go back to isometric view. So this looks good. If you want, you can unpin your tabular data. And now let's solve and retrieve our results. So the best way to do that in the fastest way, rather than constantly right clicking here on solutions, constantly right clicking and entering these, we can simply stay within our solution toolbar and come under thermal and simply add temperature, add total heat flux, and add a directional heat flux. And for the directional heat flux, make sure it's selected, and let's change the orientation. So definition, type, orientation here. Let's change from x-axis to y-axis. With that done, we can hit solve right here from our ribbon. The computation for the transient thermal is completed. So let's click on temperature. Let's change our visual from isolines to contour bonds or smooth contours. Okay, and it can visualize our temperature distribution, also our heat flux and the directional heat flux. Okay, so for the directional, we can always change it back to the isolines. And let's navigate back to our temperature, and if you hit graph, let's pin that, and then you can make it a little bit bigger, and you can see the changes in the temperature distribution and also the heat flux and the directional heat flux. And then you can always make it a bit smaller and then unpin it. Okay, so this concludes our study of the transient thermal analysis, and we'll go to the third study, which is the thermal stress analysis. Let's begin our third study, which is the thermal stress analysis. So let's navigate back to our project schematic. Okay, and now we need to drag and drop a static structural analysis into the steady state thermal analysis solution. So let's navigate to Toolbox, Analysis Systems. Let's scroll down and let's select the static structure, which is here. Hold and drag and drop it into solutions of the steady state thermal right here. This creates a static structural system that shares the data from the steady state thermal system. The temperature distribution from the steady state thermal analysis is now the load input for the static structural analysis. Alright, now let's add some more material properties. So let's double click on engineering data in the steady state thermal cell. Okay, so here, steady state thermal, engineering data, double click on that, and let's add a Young modulus. So let's click here, make sure you have aluminum, okay, and let's click on material field variables, and let's navigate down to linear elastic, okay, and let's add a isotropic elasticity. Okay, so once we do that, we'll now have the option to input our Young modulus. So let's double click here and let's enter 70. Okay, well, this is pascals. Okay, it should 70 gigapascals, and that will be 7 to the E plus 10. Okay, so that's pascals, and that will be 70 gigapascals. All right, and also for the Poisson ratio, let's make that 0.3. All right, and also we need to add isotropic instantaneous coefficient of thermal expansion. So let's click on material variables, make sure aluminum is highlighted here, and let's go up to the physical properties and isotropic instantaneous coefficient of thermal expansion. Let's double click on that. And for the values for that, here let's enter 2.2 e to the minus 0.5, enter. Okay, let's change the units here. So let's click here and let's take back our units to metric. So we'll work with the Celsius for this one. That looks good. So let's close our engineering data and let's double click on setup for the static structural analysis. So here, let's double click on setup and let's click yes here, and this will start our mechanical. And now we can go ahead, once mechanical is loaded, we will go ahead and set up our static structural analysis. Now mechanical is fully loaded for us. Let's scroll up and let's minimize our previous studies, which is steady state thermal, transient thermal, minimize those, and we'll focus on our static structural. Let's firstly right click on static structural, and we're going to insert a fixed support. Okay, and this will be at the base, so make sure you have the face filter selected here. Select the base, apply, and you can always right click and go back to isometric view when you're finished. Now let's solve and retrieve our results. So let's go down to solutions, just click on solutions, and then we'll add a total deformation. So click on deformation in the ribbon, and we have total. And also let's navigate over to stress, and let's add a equivalent Van Mises stress. Okay, and we can simply now hit solve. So if we go to our solutions here and click total deformation, let's take off the vectors, and here we can see our total deformation. Let's click on the graph and let's pin it, and let's just hit play. Let's minimize this. Well, it can't be minimized while running, so let's stop. Let's minimize it, and let's hit play. And you can see the expansion and contraction of the heat sink over the period of time. Let's stop it, and let's navigate down to the equivalent stress. And here you can see the equivalent stress on the base. Let's navigate back to our project schematic, and let's drag and drop another static structure into the model of our steady state thermal. Let's now double click on setup within our static structure, and let's rename our static structure 2. So let's click here and let's hit F2 on our keyboard, and rather than call it static structure 2, let's call it static structure uni, and I will use underscore, and I will just say temp, enter. Okay, now let's right click and go back to isometric view, and let's close the previous, and let's just focus on the static structural uniform temperature. Let us right click on static structural uniform temperature, and let's insert a thermal condition. Let's navigate to our filter, and let's select body, and let's select the body here and hit apply. And for this, the magnitude, let's enter 10 degrees Celsius. And also let's add a fixed support. So as we are already in our environment for the static structure, we can just simply go over to support here and click fix, and fix support is here. Now let's rotate. Let's look for face, select face, and let's click our base and apply. Right click, back to our isometric view. Now let's select solution, and for solution let's add the total deformation, so deformation total, and also for the stress, let's go to stress and equivalent stress. Okay, and let's just hit solve. Let's go to our solution and select total deformation, and here we see the total deformation and here the equivalent stress as well. So the distribution of these are shown with a temperature increase of 10 degrees Celsius. All right. Within this lesson, we completed 3 studies. The first one was the steady state thermal. The second one was the transient thermal. And the third one was our thermal stress analysis. And we also did a temperature increase, a uniform temperature increase. And this concludes our study. Thank you for tuning in. Take good care and bye for now.